Hi, this is Terry Kujma here at Penn State University, and what we'd like to go over today is materials and nanotechnology bottom-up manufacturing, and we want to take a look in our first lecture at surface wetting and adhesion. So here's our outline for today. We're going to do an introduction. We're going to look at some definitions that would help us understand the complexities of surface wetting. And we're also going to look at some examples that we're going to show that example. And we can take a look here, just on my outline slide and some artistic rendering here. On the left lower corner there, that picture is the lotus leaf. So that's a natural material that is used as an example how well it sheds water, so you can see the water shedding on there. And then on the right we can see a schematic picture that shows us actually defines wetting. So we could have bad wetting as a degree over 95-degree angle. You can see how that droplet is interfacing with the surface, and then we can consider good wetting less than 45 degrees in the middle picture, and then complete wetting is down on the bottom at 0 degrees. So again, what we're looking at is the real relationship here is we have a known quantity. Usually the wetting solution is water, which happens to be polar and offers us some ability to spread bonds. And basically what we're examining is the surface energy. So in that diagram, we could see that the first material on the top that has the 95-degree angle has very little surface energy. Therefore, the water doesn't want to spread out its bonds. There's a moderate amount of bonds on the surface in the middle one. That's why the water droplet is spreading out more. And as on the bottom droplet, we can see that there's a tremendous amount of surface energy, and what that's going to allow us to do is spread out those polar bonds across the surface. So those are just some artistic rendering, quick pictures, but they do tell a lot about what we're going to be doing in this presentation. And again, the picture on the left, often what we do to look at wetting and wetting principles, we can always go back to nature, because nature uses wetting per se or non-wetting as sometimes a low energy tool to get some work done. So let's look at an introduction here. Wetting is the ability of a liquid to maintain contact with a solid surface, resulting from intermolecular interactions when the two are brought together. The degree of wetting we'll define as wettability is determined by a force balance between adhesion and cohesive forces. Wetting deals with 3 phases of matter: gas, liquid, and solid. Adhesive forces between a liquid and solid can cause a liquid drop to spread across the surface. Cohesive forces within a liquid can cause the drop to ball up and avoid contact with the surface. So that's the one we're going to look at for the most part in this presentation the most. So let's look at some more angular dependence. The contact angle theta is the angle at which the liquid vapor interface meets the solid liquid interface. The contact angle is determined by the resultant between the adhesive and cohesive forces. As the tendency of a drop is to spread out over a flat solid surface increases, the contact angle decreases. Thus, the contact angle provides an inverse measure of wettability. So this diagram, what we're looking at shows the boundaries between the different interfaces. So we have alpha, beta, and the theta interface, and we can look at these equations, and these equations are going to show us the components of net force that are driven along the particular axes. So these 3 equations will describe the interface at that particular juncture. So we can also take a quick analysis and explain these relationships through a standard diagram called the Newman's triangle. The Newman triangle is a consistent with the geometrical restriction that alpha and beta and theta equals 2 pi, and this applies to the law of sines and cosines that produce that relationship. So this is the relationship describes how the interfacial angles depend on the energies at the different surfaces. So we're looking at all those surfaces and the angles that they make between them, allowing us to extrapolate the energy at that interface. So let's take a more detailed look. If we look at the beta phase and we replace this by a flat rigid surface, then we can consider that beta is approximately equal to pi. So the net force equation simplifies into the Young equation, which relates the surface tension between the three phases of solid, liquid, and gas. So this equation also applies if the gas phase is another liquid, which is immiscible with the droplet of the first liquid phase. So this is the schematic drawing done on the lower right, and we can see the equation here with the representation coupled to the drawing. So here's Young's equation. What this shows us is the contact angle, or the cosine of the contact angle, is equal to the surface free energy, and we're going to call that gamma SG, minus the free energy of the liquid solid to liquid interface, gamma SL, all divided by gamma LG, which is the free liquid of the energy to gas surface. So this gives us the relative energies and interfaces at that particular angle. So this is, again, Young's model, and we can see this is the interaction between the water droplet and the solid surface, and this number is dependent on the free energy of the surface, with the different physical states surrounding the water droplet, which we would consider the ambient of the environment. So let's take a look and define how we would say basically the energies at the interface, or what the angles mean. So we would consider a low contact angle less than 90 degrees. And this usually indicates the wetting of the surface is very favorable and the fluid will spread over a rather large area of the surface. For a high contact angle, we would consider these numbers greater than 90. This generally measures the wetting of the surface is very unfavorable, so the fluid will minimize its contact with the surface and form a more compact liquid droplet. So if we would look at angles that are greater than 150, we could term these super hydrophobic surfaces. So these show almost no contact between the liquid drop and the surface. And indicative of this is on the right-hand side is the water forming off of a back on a duck. So here's the angles. We can see the picture on the top. We can see a side view photograph of the water interfacing with the different surfaces, and we're describing actually the angle that they make. And then we can define the strength of the solid-liquid interactions and the liquid-liquid actions. So we would see for the contact angle theta equals 0 in A, we would have perfect wetting. The liquid to solid interactions are very strong, and the liquid to liquid interactions, the drop itself, are very weak. If we would look again at the other between 0 and 90 degrees, we would have high wettability. The liquid solid interactions could be strong or weak, and the liquid interactions could also be strong or weak. We can also see the other angles on there and take a look at their relative strengths. So as an introduction, we have to understand and modify adhesion as a common thing that we do in engineering, and is a huge area of research. So the applications and demand of this area are very broad. This series of lectures that I'm going to complete in this note packet are very broad, and they define the need to explore various methods to control adhesion. So historically, some of the first research was done by Young in the early 1800s to understand, the world around him, what he was seeing. So we would like to understand adhesion in as far as chemical affinity, adhesion properties based on morphology, adhesion properties that include electrostatics on a surface, and then certainly we would like to look at characterization methods that are associated with adhesion properties, such as we shown before. We can extrapolate surface energy looking at the angle that a water droplet would make with the surface. And certainly we want to look at some mathematical constructs to help us understand the process and help us better understand how the material is manufactured. So what we're going to do in this note packet is introduce some basic concepts and add some additional concepts to get a full picture of the engineering possibilities and what we can do with materials on the nanoscale. So these are some, if we look at the timeline of technology with results of the idea of looking at the study of water. We would look back in 1805 when Young developed his famous equation, and then we go forward into the early equations from Wetzel in and around the beginning of World War II, well, before World War II, in 1936. And then we would look at how this would take us to other areas that chemists would use these different processes, and they would develop materials such as PTFE and PDMS. And certainly material that we look at interest, we look at both of those materials of interest within the nanotechnology program here at Penn State. Then further, as characterization became more common and the detailed look at wettability became more deep, we look at the Casey-Baxter equation developed shortly before the end of World War II. So these led to some foundational developments, I guess, in modern thin films, to where we would look at other things that nature had to offer, such as the lotus leaf and the foot of the gecko. So again, this is a nice timeline to take a look at the impending technology of wettability. And these also show famous equations such as the Young's equations, the Wetzel equation, the Casey-Baxter equation, and other introductions of the mathematical constructs that help us understand superphobic interfaces and re-entrance of surfactants at the surfaces. So let's take a look at hydrophobicity and define where that word comes from. So hydrophobicity comes from the word hydro, which is water, and phobicity, which is fear. So hydrophobicity is simply the fear of water. So this is what we would use to describe water beads that do not like the surface. So this gives us an angle of greater than 90 degrees. So we would consider that this material is hydrophobic. We can also take a look at other materials, not just in the water realm, but we can define a term lyophobic. So this is more defined as marked as by lack of a strong affinity between a dispersed phase and in one liquid, and which the liquid is dispersed. So what this does is allow us to have a different material that's not water or oil. We would consider this as more of a generic term called lyophobic. And then there's oilophobic, which is having a relative lack of affinity for oil. So that one specifically refers to oils. So generally within this presentation, most of the time I'll be referring to hydrophobic, but when appropriate, I'll be discussing lyophobic and oleophobic principles. In the same phase, we would look at materials that would have, or an interface that we would not like to have wetting. So this would be hydrophilic, and would like to have wetting. So this would be hydrophilic, which means we'd have a strong affinity for water. Lyophilic, which is a mark for a strong affinity between a dispersed phase and a liquid in which it's dispersed. And oilophilic, which is relating to a strong affinity for oils in an interface. So just like the phobic systems, there's also a corollary opposite terminology for the same three sets of conditions, which would mean a strong affinity. So let's go ahead and continue our discussion on definitions and example. So we can define the adhesion. It can be influenced by many factors, not just the simple factors, but a multitude of factors. It could be the surface liquid chemistry or other phases. It certainly could be the surface morphology. It could be a combination of the morphology and the chemistry, and we can look at this as an example in the lotus leaf. We can also have other influences such as electrostatic forces, such as van der Waals interactions, and we can define this by looking at nature and what it shows us with the setae on the gecko foot. And then what's very complicated is we can have a multitude of these forces simultaneously. So we can get dominance from one or more of the, relative dominance from a multitude of these forces at once. So here's a lotus leaf, and this is certainly an example of the solid liquid gas interface. So we have the solid being the lotus leaf, water being the liquid, and gas is the air ambient around the leaf itself. So we can see that the water beads on here, and this system is very hydrophobic. And what helps on this system, and what people like, is they often refer to the lotus leaf effect, that we would be able to create this on man-made materials or apply coatings to man-made materials so that we wouldn't have wetting on that particular material. This, for example, could be good on systems such as airplane wings, because we wouldn't build up moisture and ice, etc., on airplane wings, which certainly could be dangerous and or reduce the efficiency of the airplane. It also takes time to clean off airplane wings in the airports in the winter, so this could be used for that. It also could be used for materials that are self-cleaning, like windows on a building, that you wouldn't have to pay people to clean those windows, so that would help out quite a bit. So those are some examples that we use, man-made examples or areas that we would like to use from the example of nature. So here's some more angles. We can see that the lotus leaf is typically, the angle is greater than 150. And what we can see is the model on the surface is not only is that surface have a certain chemical affinity, such as oils on there, but it also has a certain morphology on there that the water droplet actually sits on. I guess you could call them something that looks like small hairs. And these small hairs are on the order of 10 to 1 microns in diameter. So they're actually very small, and the water droplet will sit on top of them and won't be able to wet the surface. This also lends us to what that will do. Now, sitting on that the small surface with protruding wax crystals, which would be a chemical layer on top of the epidermal microstructures on the surface, things like water will roll off the surface. And when water rolls off the surface, interestingly, water has an affinity. It's polar and has a chemical affinity to combine with materials. It will simply wet the materials. What this will do is be able, the water rolling off the surface will clean debris off the surface. So this is a self-cleaning system. We can also model this mathematically, or in the past it's been modeled as the Casey state, where the water droplet actually sits on these small structures and is supported by these small structures, prohibiting wetting on the surface. So what this does is it keeps the water from wetting on the surface, and it's able to bead off rather quickly. So I guess this is the goal of a lot of people, to have a self-cleaning surface that doesn't wet. We can also look and see this on FESEM images, and actually this FESEM image was taken in our lab of a lotus leaf, so we can actually see those small nanostructures on the leaf itself here in this drawing. So we can see the scale bar on here being 10 microns, so you can get an idea of how small these structures are and their ability to roll water off the surface. This is also a more enhanced version. We can see down here in the lower left-hand corner, now the scale on here is 2 microns, and we can actually see the smaller structures on the surface and how they're going to support the water bead and not allow the water bead to fully interface with the surface. So basically the bead is riding on top of the surface in this case. So with that, I'd like to wrap up this quick first lecture, which is an introduction, and again, look to nature and see how nature does it. For example, and this was basically a overview introduction to see how wetting impacts us, and certainly wetting is a huge material engineering concern. So on the next one, what we're going to do is take another deeper, more detailed look at material interface forces, and we're also going to look again at nature. So the next time, what we're going to do is look at examples of wetting from the perspective of the gecko foot. So I'd like to thank you for your attention, and we'll see you in the next presentation. Take care.